Hey everyone, this is Michael from Bart Musical Circuits. I'm going to today be going over the BMC110 rhythm to voltage converter. I'm going to start the description looking at this shift register over here. So there's two of these in the circuit. There's one over here as well. They're set up the same way, so we'll just look at one of them. And the clock and reset inputs are exactly the same on both of them. So I'm choosing this one because this actually has the pull down and diodes here. So if you're not familiar with what a shift register is, this is a chip that it has a clock input and a data input and then several outputs. When the clock input is struck, it's going to look at what's on the data input over here and then transfer it to the first output. Then whatever was on the first output gets transferred to the second, third, fourth. We're using CD4015. This is a dual 4-stage shift register chip. We've just wired it as a single 8-stage shift register. As you can see, the data on the fourth comes through here to this diode to the data on the second set. And I use this diode and pull down resistor. It's kind of over-engineered, but it's there to make sure there's no interference from how you're patching this fourth output to mess with the data that's going to the second set. There's clock and reset pins. Each of these has a diode that's going up to plus 5 volts to do over voltage protection, and then a 10K pull-down resistor. And these are getting signal from these comparators over here. So yeah, well, and our data is also coming from a comparator that's set up the same way, and we'll look at those after we go over some other parts of the circuit. The outputs of these are all set up in pretty much the same way, except for number 8. And so we'll look at number 8 first, actually. So what makes 8 different from all the rest is that it, in addition to going to the jack and the LED and the digital to analog converter, it's also going to go to this toggle switch down here, which this is our normalization toggle or our loop toggle that sets loop points to feed the output of number 8 back to the input, so you can create a loop from this. And you can also set it to go to the input for the other 8-stage shift register, and that's how you get these 16-stage ones. But yeah, each output, there's a 1K that goes to the jack. That's there to protect the chip and your power supply in case you patch it straight into ground or something crazy. And then there's a 22K going to the LED. That 22K is just going to set the brightness for it. I didn't want to go too bright with these because there's so many LEDs, you don't want it to be blinding, and you don't want to take up too much current. And then finally there's the 200K. And that is going to this R2R ladder. So it's called an R2R. It's made up of 100Ks and 200Ks. 100K is R. A 200K would be 2R. And basically this is a very fancy kind of voltage divider that we're using to create our digital to analog converter. So, you know, a basic voltage divider, if you had 5 volts, 0 volts, they're both the same value of 1. You get 2.5 here. If you change this to a 2 instead of a 1, then it becomes, oh gosh, I think that's 3.6. That's me without looking at a calculator. I think 2/3 of 5 is 3.6. And that's exactly what would happen in a situation where the first output is high and the rest were low. It would be 5 volts over 0 volts. But that then gets repeated over and over again. The voltage here is the result of either 5 or 0 here over whatever this is, over that. And so it keeps getting divided down smaller and smaller. So this top one is going to have a much bigger influence over the voltage than the bottom one, which is how binary numbers work. There's a most significant bit that when that bit is active, that's doubling your voltage. And then there's a least significant bit, would be this one down here, and that one is going to be setting your voltage. That's going to make the smallest amount of change to your voltage. So yeah, the voltage that we get off the ladder then goes to this op amp here, and this is set up as a non-inverting op amp with a gain of just a little bit over 1 that gets set by this trim pot here. So this is adjusting the amount of feedback that the op amp is sending back to its negative input, and that's setting the gain. And again, a 1K output resistor for it. Oh, and I guess I haven't mentioned it. These little wire pads here that say 22 or 123, these represent the connectors between the two circuit boards, and the yellow highlights, these represent things that are on the bottom circuit board rather than the circuit board with all the chips on it. So yeah, I mentioned the normalization. Let's look at the inputs for these. We'll go to up here. So we had diodes coming off this, and as you can see, our right button, our two data inputs, these have diodes on them too. And so all of these diodes are going to meet up here. So this is never going to be more than 5 volts, no matter how many signals you're pressing on it. And it also has this 100K pull down resistor. Then this diode is passing that on to the next stage, where we have our erase switch, which just connects to ground. Much like our right switch connected to plus 5 volts. I guess I skipped over that a second ago. This will then ground out all of the signal from these. And so, yeah, with that, you're able to input signal or erase signal that's going to it. And then that meets it up at this comparator. The comparator has its threshold set here. It's very low threshold voltage. So that would be, I think, 0.5 volts, which if you're sending in 5 volt gates, that should be fine. We set it that small, so also just the very first rising of a waveform, like a triangle or a sine, would also hit it. And the output of the comparator, like all of them, goes through a 22K, which combined with the 10K pull-down resistor is going to attenuate the voltage down a lot. And then the plus 5 volt is there as just overvoltage protection. Now we have our clock and our reset inputs down here. We'll look at the reset first. Here we just see we have our jack for the input, and then the button, that the button just connects to plus 5 volts, and then a 100K pull down resistor going into a comparator. Very simple. 2 different ways you can trigger the reset. The clock is similar, except we have this capacitor here as well, and we have to have another resistor because of the capacitor. So doing it this way, it's always going to be a very short pulse, either from the button or from the gate. This 100 picofarad and this 100K, these are going to form a high-pass filter. So you're just going to get a very tiny pulse at the front and a very tiny pulse at the back if you're inputting a pulse like that. And then the comparator is only going to pay attention to the pulse that's going above 0 volts. And that's basically it. It's a module with a lot of jacks and a lot of functionality, but not actually that simple. It's just a lot of things that are, none of them are really that complicated. Our power section's up here, and it's pretty much standard. We have a 5 volt voltage regulator here, power connectors over here. We have the plus 15 volt connector here. That's part of why we have these diodes going to plus 5 volts, is because if you were using a different power supply besides 12 volts, that would give you some protection to make sure that you're not going to over voltage things. Thank you for watching. I think that covers pretty much everything.